it doesn't have its own network namespace at all. It's just got a copy of the host namespace. So we haven't met all the requirements. So how do we fix that? Well, we'll shut this thing off. And we'll go back to our Makefile. And this is where we need to be able to launch it in such a way that it has the attributes we want. But because we're doing it in the Makefile, it's for testing purposes, right? It would be weird to use the Makefile as a way to control the actual container on a host. So what do we have to do to launch this container in an actual namespace network unique container? We're going to go to the IP command, and we're going to say IP network namespace. And we're going to add a new namespace that's the same name as the container. And then we're going to have to do more steps. We need to create a pair of virtual interfaces. So one will be called mvps- the name of the container. And this is going to be a type of virtual Ethernet, which with a peer name, meaning create two interfaces that are linked by a virtual Ethernet cable, essentially. And I'm going to call the peer MVPS. This totally works wrong if you don't type it right. Dash name. So we're creating two interfaces, an mvps-web1 and an xmvps-web1, and they're linked via virtual Ethernet cable. So we got those two interfaces, and the next thing we're going to need to do is we're going to take the xmvps one, and so that's the one that will be slated for going inside the container, and we're going to reassign it to the container's network namespace. So that with Ethernet interfaces, they can only be existing in one namespace at a time. So as soon as you set it to a new network namespace, it vanishes from the one it was in before. So Ethernet devices can only exist in one namespace, which is why we made two with a virtual cable between them, so we can put one into the container's namespace, have the other one to plug into something. So we're going to say, OK, IP link xmvps name assigned to namespace, which will be the container's name, the variable here. All right, so once we've done that, now we can plug the other end in, and that's where the bridge utilities come in. Bridge control, add interface, name of the bridge. So to the bridge, we want to add mvps name. So this is the end we didn't put in the namespace. And we're going to set it up. IP link, set mvps dash name. It's like, why do people use IDEs with automatic variable completion? I have no idea. This is what I think. We're like, from scratch, really from scratch. OK. I debated installing like a better environment, but I thought this would be more fun for somebody. All right. IP link setup. OK, cool. So that's going to activate or bring link up on the end we plugged into the bridge. We're almost there. There's only like 30 more commands. So what do we have now? We have an interface in the container namespace. We have an interface plugged into the virtual bridge. They both have weird names. One side is link up on the bridge side. The other side is not link up. So we're going to say, now we want to start doing things to the one that's in the namespace that we set aside for the container. So in order to do that, we have to execute commands in a specific network namespace. So we use the IP netns subcommand exec. So we're saying exec in this namespace called name, and now we just put whatever command we want executed in that namespace, which happens to be the IP command again, and what we want to actually do. And in this case, we want to say xmvps. We're going to rename it to ETH0. Now, we can do that because it's in its own namespace. And because an interface can only live in one namespace at a time, the other ETH0 that we have in the host namespace will not be interfered with because they're in separate places. And this way, all the things that run in a container that, if you have to know the name of an interface, you don't want an arbitrary name. You want a name you can predict, ETH0. So we've now renamed it. The next thing we need to do is we're going to need to bring it up so it can actually be configured. So it's going to be IPnet exec again, and again in the namespace. And we say IP, link, set, and this time we just say ETH0 up because we renamed it to ETH0. And of course, we got to configure it with an IP address. So again, same prefix. We're going to just standard config command. You can abbreviate it any way you want. add an address. And here's where we put in the IP address. We put in the variable for device ETH0. And lastly, we also have to give it a default gateway. Somebody say typo? Yeah. Okay. So we got to give it a gateway, default route. So same thing, name, IP, route, add, gateway here. And we're going to say, oops, sorry, not there. Default via, there we go. So default via the gateway, so that'll give it the default route. And now we're actually ready to launch the thing, right? Because we've set it up its network, we've got it ready to go, we can launch it in there. So how do we run a command in a network namespace? Well, we might as well just keep going. There are other commands that could be used, but I think consistency is good, so we'll just go with this. And now what's the command we want to run? systemd-nspawn awn. And we're going to add an extra flag. This is the M flag, and this flag is just for giving a tag to the virtual machine or container. So this will just tag it with its own name. And then we're going to tell it, of course, what it needs to know to run it. rootfs is there. And then -b for boot. Now, remember that make will stop if this fails. And the odds of me having made no typos so far, I don't know. But if it fails, I don't want it to stop because I want to put a cleanup command next. So I'm just going to stick in here true. So this line will always pass for make, even if the machine actually blew up. Because the only thing I'm going to put next is just delete the namespace that we had created. So there's a little cleanup of that namespace. Because after my test, I don't need it anymore. All right, so that is all the stuff we'll do for testing it. Now we'll save it and see if it worked. So I should just be able to say make test. And I probably made a typo, so let's figure that out. Oh, yeah, I totally made a typo and nobody said anything. All right, because I didn't recognize it either. It goes right here, MVPS dash. No, sorry, that is correct. MVPS, we add the namespace. I forgot the word add. That's kind of a problem, right? OK, link add. That should work. So I'm going to manually remove that namespace because the cleanup didn't run. All right, let's try this again. Make test. Same thing there. Good. OK. Oh, yeah, I did the same. Right. I just did the same typo more than once because I'm consistent. All right, let's check the rest just in case. Everything looks OK. Cool. So we'll delete that namespace. And let's see if those interfaces are. Well, we don't need to add them there, but we do need a set. You're right. Good catch. All right. OK, cool. That looks clean. So we'll delete the namespace. It's gone. And let's check and see if those interfaces were created. They are. So we'll just remove those really quick. And I think if you get rid of one, you get rid of both. OK, cool. All right, third time. Here we go. Look at that. It's launching. OK, so the question is, though, did it work? So we'll log in and check the namespaces. And sure enough, it's got an ETH0. It's got the right IP. Pretty good. If I go to another terminal, let me just bring this one in. All right, and let's just see if we can ping it. We can ping it, so that's a good sign. What were our other requirements? Yeah, it should have a website, right? It's got the website, so that's good. And the last one, SSH is root. Don't need that. Boom, we can SSH in its root. It's pretty good, right? It works. Let's take a look at what it's got inside it. It's got a lot of stuff inside it. And it's probably more than we want. So that's the problem we'll address next. There's a cool tool you can use here. It's called systemd CG top, which is to show you C groups. And this also, though, lets you look at the memory usage. So I hit M to sort by memory. And right now, it's taking up about 40 megs of RAM. So that's not bad. I mean, that's not huge, but it's probably a lot more than just a web server SSH needs. But it's a good way to compare what we've got running there. All right, so we'll shut it down again. And hopefully our cleanup functional file fire off. All right, so we have basically met the requirement, right? Like that was my requirement. But I noticed in testing that when I did more than just a trivial couple of commands, the memory footprint doubled really quickly, right? Like it went up to like 90. And I only have 8 gigs of RAM in the laptop where I needed to be able to run these things. So that wasn't going to be enough. So let's review real quick, and then we'll take it to the next stage. So we created our Makefile. We just filled out some variables to have stuff that's reusable. I put comments in here so you can see we installed packages with yum. Very important that we set install root to an absolute path. If we don't do that, yum will not be your friend, trust me, because it'll just decide to use your root directory, your slash. It's weird, at least in the version that I tested, it just ignores the option if it doesn't have an absolute path, which is not good because you're installing packages. Clean up the metadata, rsync the payload. So this is really it. Like that is the container build. And all you do to customize the container image is you just put more files in that FS tree, and then boom, you've customized. How you generate those files, that's your choice. Config management, whatever, I don't know, but it's flexible. This part was the fun part to type. We got through it pretty painlessly, but this is all of the commands to do the pre-setup to launch the container, create its network, set it up in the right namespaces, configure it, and then, of course, the last command, we made sure it didn't. It would always pass, and so it has a cleanup command. All right, so we put all that in there. And then, of course, the last part of the Makefile is just a make clean. And now we have, essentially, a buildable, testable container, but it hasn't ticked all the boxes, right? It's not really easily manageable. There's no kind of deployment, nothing like that. By the way, what was in the FS tree? Just a little more detail for you. You may be tempted when automating a build to launch within the container the user add command and add users and whatever. I decided to just, again, simplest, easiest way. I just wrote out a password file, created the shadow file, created the group file, and then they just get copied in. Because I know exactly the set of software that's going to be in the container, this works. So I know which users need to be there. The http.service file is not a file. That's actually a symlink. That's just how systemd enables services. So instead of, again, having to go in and calling a check config enable or something like that, I just make a symlink here that has the right target, and it's copied in. And then the last thing is the web page's index file. Any questions so far? All right, so pretty straightforward, pretty simple. Let's see if we can get to that reduction part, right? Like we don't want or need the whole OS running in there. Instead, let's slim it down and see if we can get to somewhere in that middle ground. It's more than a single process, but it's less than an entire OS. All right, so of course, we're going to go back to the Makefile. And anybody want to guess what's about to happen? We're going to delete stuff, right? I mean, how does systemd control services? It controls services using symlinks. So if you want to make it so that none of those services start, I have this wacky idea. Just delete all the symlinks. Now, you might be tempted to just run find and look for type of link and delete everything you find. That's probably a bad idea. I tried it. It doesn't make anything runnable. The end result is not usable. Yeah, let's put it that way. So what we're going to do is we're going to do just a little bit of targeted deletion. So etc systemd system directory. This is where the administrator is supposed to put symlinks in, and the default system comes with a bunch of them. So there are these directories called something wants, and you put symlinks in there to say that if this service starts or this run target wants these links, we'll just get rid of all of them. So we don't need any of those. We're going to do a few more. Now, when you go into the lib systemd directory, you got a lot of more stuff in there, and there are several targets. So we're going to clean out the basic target because it has its own wants directory. Let's clean out everything that has. We'll do a little copy paste just to speed it up a little bit because there's basically the same thing with sysinit. So we don't want any of the sysinit wants. We'll be slightly more surgical with the next one in that this one we're going to delete only the udev files from, like, there's no reason to try to create devices because it wouldn't even have access to anyway. So we just want to speed things up, get rid of things that aren't going to run. So we'll get rid of those, and we'll also get rid of the init control socket and so forth. So we'll get rid of that guy. And we've got a few more. There are going to be local FS, which is for cleaning up the local file system. Again, it's a container. We don't care about that, so we'll get rid of those. Let's see. Two more there. And then Anaconda, for some reason, has services that run, so we're going to get rid of those. We definitely don't need that running in the container. And the default multi-user run level starts up a lot of stuff as well, so we're going to get rid of that. And lastly, back to the etc directory, actually. So we'll just copy that one. The default target that gets assigned actually points at a run level that gets completely broken when you've done all this other stuff that we just did. And so I want to repoint default target, but here I'm only going to delete it. Now, I tried to tell myself, resist all temptation to do anything in here other than delete files. Leave it to just the one-time copy for the FS tree. So don't manually create things by steps or anything like that. So assuming there's no typos, and this will delete all of these links and clean out the startup of the image. And of course, in order for this to work right now, since we've broken the system, we have to add some stuff back in. And we also have a slight order of operations issue here. So we're going to delete that rsync and put it last, because that needs to be last, is that we're going to delete some links and add them back. Right? Because we just sort of delete everything, and now we need to add a few things back. I'm going to take a slight cooking show approach here just to speed it up a little bit. And so I'm going to say, OK, let's save this. And I'm going to, again, grab a different FS tree that's ready to go. All right, so we've got the same setup again. We've got a new FS tree with some additional files that we'll discuss. And we're going to do a make clean. So we're going to wipe this out and run it again so that we know that we've built it correctly, since we made some pretty significant changes. And we're going to do the build. And so now we'll get, again, that 90 seconds of package install. And then it will do the deletions and then the additions. So let's review some of what we did while that's happening. You can save a little time. So here's all the stuff we're deleting. And again, we're deleting just about every startup symlink you've got. And this is what we're putting back. So the files that are gray were already there. The files that are in white are new. So I put a new symlink for default target. I had to change the HTTP service unit file, and I'll show you that in a second. And then I add the SSH back in because we deleted it out, but we want it to run. And there's a couple of temp file services that need to be there. Otherwise, the system just isn't functional. So this is just about done. It's verifying packages. And there, it deleted files, it copied files. Let's test it. And make a test. OK, we see it's different, right? Fewer lines went by, no more login prompt. So we know there's no Getty running or anything like that. So now what we can do is go over here. I'm going to need to delete the SSH config, because it will have a new key, because that's one thing we didn't copy in. So here now we will SSH to it so we can check out what's going on inside. All right, and we get that weird message. It thinks it's still booting up, because again, we cleaned out the boot process so much that it's not doing the normal maintenance where it creates the files to let itself know it finished a run level target. But do we have our network? We do. What's running in it? That's much smaller, right? So now if we look at what's actually running inside this container, systemd is the parent process. We've got the systemd journaling service, because we probably want to get logs, and there's different ways you could approach that. We've got Apache, SSH, and dbus. Now, one of the interesting things about systemd is that because it has this whole dependency resolution process, you will find things here you didn't link. And that's because if one of the units you did run, like HTTPD, has requirements, systemd will fire those up, even though unless you go and delete their unit files, they will get fired up. And probably needed, but you can do your own analysis to figure out what's actually needed. So that's pretty good. That's up and running. Now, of course, we could do our test and see if the web server still works. And it does. And we saw that SSH works, and we know ping probably works because I logged in. All right, so I mentioned I had to change this file. This is the service file for HTTPD. It just, when I did exactly what I showed you guys, but without having changed the file, it just didn't work. It would not start. And trust me, this was fun to figure out. I had to add that because it's a dependency that Apache has. Now, what that service does, if you're not familiar with it, it creates what are called the volatile directories, and that's var run and /run. And Apache wants to write its PID file into var run HTTPD. And guess what? If that service doesn't run, var run HTTPD doesn't exist. So Apache silently fails. Like, it literally silently fails with no error message. It just doesn't run. So I quickly straced it and saw, oh, it's trying to write to a non-existent directory. OK, what creates that? And then like 6 hours later, I've added this line. All right. So we've slimmed it down. It's now pretty small. Let's make it deployable and manageable in some way that we could actually do this outside of a Makefile. Oh, real quick, I'll show you the memory footprint because we want to see how we did there. What do you think? Improvement? Yeah, it's down to 13.4 megs. It's pretty tight, right? That's, especially since it balloons to 90 really quick, that's much more usable. I'm starting to approach the possibility of running 50 virtual servers on this laptop. And actually not this laptop, because that virtual machine has 2 gigs of RAM, but an actual PC laptop running Linux, sure, no problem. I've got enough RAM there. All right, so how can we make this deployable and something that we could actually manage and have repeatable builds? One of the things that's fun now is because we can't log in and halt it, we have to kill it just by killing the process. So I'm just going to find the process, kill it. You'll see that it actually did shut down correctly. You notice the end spawn receives the kill signal and then tells the OS, OK, shut it down. Most of the shutdown logic, though, has been removed, so very little happens. All right, so how do we make this thing deployable? Well, first thing we're going to do is we're going to make a directory where our containers will live for production. All right, I'm just going to call that home MicroVPS. And we'll get back to our Makefile. We need a rule to install it, so we'll do a make install. And our install target, this is going to be really simple. First, we're going to say make the directory. And this is going to go, we don't have this variable yet, but we'll call it install path. And it's going to create a directory in there called name. And again, this will give us a tiny bit of protection that if it already exists, it'll fail. What's the best way to copy files? How about CP? So we'll just say root. And we want to copy in to that install path. Let's just copy and paste here for fun. Is it faster to do that or type? I'm not really sure. And then we need two more things. We need some way to manage it now. So I'm going to say, let's copy a non-existent file, which will be called name.conf. This will be a config file for the container. And again, we'll copy to the same place. And we're also going to need a unit file for systemd if we're going to use systemd to manage this thing. So this will be a name.service. And again, we'll copy to the same place. And if we want systemd to actually know about this, we have to put a link somewhere where systemd looks for service files. It's not going to look in this directory. But it loves symlinks. So we just make a link. And the target of the link is going to be install path .service. So this is just the file that we want it to point to. And of course, where does this go? This goes in etc systemd system, which is the directory that where administrators are supposed to put links and things. All right, so that should be enough to install it. Of course, we do need to define that install path variable, or it will fail miserably. And that was the directory we created. All right, so we've got that defined. Then the last thing we need to do, or second to last, probably, there's only two more things. We need to create those two files. And so that the install doesn't proceed without those existing, we'll put them here as requirements. All right, so now we need to create those targets. And I don't know why I didn't just provide this file in advance, but for some reason I thought it would be a good idea to have it generated dynamically by the Makefile. So we'll just bang this out real quick. But the idea is just to create a config file that we can source into the service file so that it can easily be tweaked without having to rewrite the service file. So we're just going to say, generate a file called name.conf, say name equals, and we'll put in the name variable. And we'll say same thing over again. For rootfs, we need to configure that. And these are all things that will become variables inside the systemd unit file. Let's see. Just copy and paste this one here. So what is the rootfs target going to be? It's going to be that, followed by that, rootfs, right? So we're just saying put that in our template. We'll put it in quotes just because that feels like the right thing to do in case I have weird spaces in my file system. Oops. All right. It would be a terrible mistake to put a single angle bracket there, wouldn't it? All right, we just have a few more. So the bridge also needs to be configured. And this will be, of course, the bridge. Two more, IP address. And last one, gateway. All right, so that takes care of the config file. Last one we need here is the service file. And for this one, I actually, the service file, believe me, you'll see it, there was so much opportunity for typo that I decided we should build from a template. So this file will actually, it'll just be a sed command. Everybody likes sed, right? So this is the systemd configuration flag or item that you configure. There's this environment file, and that's what we want to point to this comp file we just made, or this config file. So we're just going to rewrite that to be equal to, and anybody want to guess what goes here? Our config file that we're going to install. Right? So that's going to be, once again, basically this, but with the conf. All right, and this sed command is the last command, but conf. And we're going to write that out, read it in from a config template I made to save on a bunch of typing. And we're going to write it out to the service file we want to create. All right, and we will make sure that the template's there before we do anything, just to prevent it from running for no reason. All right, that one should be good to go, assuming there's no typo there. Looks good. Anybody see anything? Yeah, I do. All right. Yeah, we're missing that. All right. I think that's good. Look good? Let's hope for the best. So we're going to save that. Of course, the template doesn't exist, so I'm just going to copy that in real quick from the previously prepared one. All right, so we've got our template for the systemd service. We've got our fs tree. We updated our Makefile. We should now be able to just type make install. Everything works. We'll find out. Looked good? OK, so how do we know it worked? Well, first thing, we can just test it by calling systemd control and saying, what's the status of this newly created service? And that's good. That means it recognized the unit file. So it says, OK, you've got a service. It's dead. We expect that because we never started it. So how do we start up this container now? Anybody? Yeah, systemctl. Start web 1. And if nothing happened, that's good. Right? Like, the only thing that could happen there would be an error. So now if we check status, you can see it shows that it started up. Some interesting tools, because we use that -m to tag it, so we can use machine control and see that it's running there. And we can use machine control and ask for the status of it. And what's really cool about this is that systemd tools are aware of containers that are running systemd inside them, right? Like Inception. So what it's done is it's actually looked into the container and asked that systemd for the status output, and that's what we're looking at here, so we can see what's running in the container. So that's a pretty handy way to run containers. You know, it's going to have the same memory footprint. We could run through the tests again to validate functionality, but we changed nothing in it. So it's probably working. You know, if this was a production environment, I would do the tests again, I promise. For reals. All right, so let's review that last part that we did. We created a place to deploy our containers. We created an install target, which just makes sure there's a couple files we need and copies them to our deployment directory. We used printf within the Makefile to generate our little config file, and I'll show you that file in a second. But the idea here is if you wanted to change the IP address of the container or something like that, you would just change it in the config file. And the config file is very simple. It's not a new thing I invented format-wise. It's literally just what systemd calls an environment variables file. So it's just a set of key value pairs that systemd loads into the environment for the container. Or, and this is the cool part, its own service file. Like that's the key, right? If you give an environment variables file to systemd within a unit, it will load those variables into that unit file so you can make it into a template. So here's the part that makes the actual unit file. So this is what the config file looks like. Again, that's just a set of variables for systemd. This is what the service file looks like. So remember all the commands that we had to run to set up the namespace and the network interface and all that? Well, guess what? We still have to run them, right? Like that didn't go away. So what we've done is instead we've asked systemd to run them on our behalf before it launches the container. So it has this directive exec start pre, And if you list a command there, that command will run before the container is launched, and they run in order. And if you put a hyphen in front of the path to the command, that tells systemd it's optional. So if there's a failure, it'll keep going. But in my case, I put no hyphens, so they're all mandatory. So if any of those commands failed, systemd would stop, and when you did the status of the unit, it would show in the output the last one that ran and that it failed. And so you could troubleshoot, it's not too bad. Bottom there, kill mode equals process. The normal systemd behavior is when you kill something, so every unit gets its own C group, so that if the unit spawns a bunch of processes in there, it doesn't matter. But the normal behavior of systemd is to kill every process in the C group at once. All right, now that's okay. I mean, it says, but what we want is we want to give an opportunity for the container to shut down. So when you say kill mode equals process, it doesn't change. This is a weirdly named option. It doesn't change how it kills things. It just only targets the parent. Right? So the one process that you told systemd to launch, it sends that one a kill, and then it waits for a timeout. And so this gives the container opportunity to shut down when it receives the kill, because otherwise it would just kill it all, which probably works most of the time, but I think this is cleaner. So again, that key part, the environment file, that was the config file, and that's what it points to. And just so you can see, these are all the places where the variables get plugged in when the environment file is sourced. All right, and that's all the stuff I tried to avoid typing this time. So one final bit here, we have a little bit of time left, is we haven't done any resource restriction. Right? Like, how would we actually go about restricting the resource use of this? Because we've put it in a container, we've restricted its view of the world, but it's getting a normal share of CPU time and unbounded memory. So let's do that, and it's real quick. We'll do some resource restrictions on it. And it turns out to do this one, you're just going to edit the unit file itself. Now, I discovered after much head scratching that the one exception to the variables are these. You cannot use variables in these directives I'm about to show you. So it's very simple. Let's say we want to limit memory. We just ask it to turn on memory counting, and we put in some kind of limit. That's it. If we now restart the unit, we reload systemd, it will impose these rules. So I'm going to say systemd stop that container. And you'll notice it actually tells me, hey, you might want to reload. There appear to have been changes. And there are, so we'll reload it. And now we'll start that container. And you could take my word for it that it's working, or I could try to show you. The way I check this kind of stuff is if you do show, it's going to show you all the attributes of the unit, right? And so rather than trying to look at all that, we'll just grep. And you can see it's now got those attributes set. So there's now a memory limitation on the container. So that's easy. And you could also do CPU. Although CPU, you're either going to pin it to a certain subset of CPUs. You're only allowed to use this one core or these few cores. Or you can also set CPU timeshare, because systemd slices up CPU time evenly across all units by default. So right now, this whole container gets its own even share. The default weight is 1024. So you just set a memory weight of either higher or lower than 1024. Sorry, not memory, but CPU weight of higher or lower than 1024 if you want to use weights to adjust how much time it gets within something smaller than a single core. So you saw the unit file. We put in the memory accounting and the memory limit. Very simple stuff. Man systemd.service if you want more information on that, and systemd.exec. Any questions about any of the stuff we discussed? So we succeeded. We took a minimum CentOS install, freshly made, and in enough time to come in under budget. We've built a working container system. And it's my pleasure to be here. Thank you very much. Questions? Question?
Yeah, could you give like the 30-second version of network namespaces, or if that's not possible, how you were running a systemd command under IP?
Yes. So there's two things about that aren't exactly what they look like. So just really quick, when you type IPL and you get a list of something, that's a network namespace, right? And that includes your copy of the firewall, IP tables, and the routing table. So if I create a new network namespace, it's a whole new set of those things, and only processes in that namespace can see and use them. All right, so that's a network namespace is, there's probably a better word than namespace, but that's what we use. So it's a like network environment you might think of. So that's what the namespace is. Now the IP commands, when you say IP net namespace, so you're calling the namespace module exec, what you're saying is, I'm going to give you a namespace. The next thing I type is the command you should execute within that namespace. So it can be any command you want. Now here's the part that's a little bit of a brain fuck. Sorry, it just is. Processes on Linux with this modern kernel and namespaces, it's multidimensional, right? So any given process can run in any set of namespaces that may or may not overlap with another process that is using namespaces. So for example, that container has its own root file system namespace, its own tree, its own memory lockdown. That's the C group. It has its own network namespace, has its own user namespace. So if it looks for user IDs, that's separate, all that stuff, right? This command, if I do the net exec, it's only using a network namespace. So if the next command I type is IP something, like IP link, whatever, it's not running the copy of IP from the container directory. It's running the normal system IP command because it's still the same file system, the host file system namespace. It's just running that in this network namespace. You feel that? That's the brain fuck I was talking about. That's just how it works. And it's like if you're a programmer, it's an array of arrays. Look at it that way. If you just have trouble thinking about it, it's really just that this is how it works, and you get to choose exactly how each process runs. Like that's what it comes down to. So we have a couple of more minutes, like one. I'll show you one thing I kind of wanted as a bonus. So if we reviewed the requirements, I think we met them all. What do you guys think? Yes? Fair enough? Yeah, fair enough. So I just was curious, though. Can we shrink this like even smaller? And so I tried it with BusyBox and DropBear, which is a tiny little SSH server, just to see what that would result in. Rather than typing it out, I'll just show you what it looks like, since we only have a minute here. But BusyBox requires you to set up the whole file system, so a bunch of make directory commands to set that up, and some change mode, permissions. You have to install the BusyBox binaries, and then you have to run and generate all these symlinks to point back at BusyBox for all the commands that it's going to represent. This is installing the DropBear SSH server. So again, it's a tiny little SSH server, uses a few symlinks. You have to generate the keys because it has no startup script because we just made this whole OS from scratch. So there's no init system. So you generate the keys. Here's how you download those two things. And I have one that I pre-baked, so I'll just show you. Is that 4 or 5? That's 4, right? Yeah. We'll find out. 5. No, it's the next one. All right. I pre-baked them all just in case, Little things. All right. Thank you. All right, hang on a second here. What did we do? Oh, we're already in there, right. All right. Is this the right one? Yeah, that's it. All right, so because we're not doing any kind of package installs or anything, it should build really fast. It just has to download BusyBox, which is not even a meg. So this, I don't know why it's slow. There we go. And the drop bear server, build it. I copied the time zone files straight from the host. So that's what that has there. Let's check. I just want to see what IP we gave it. 25. OK, so make test. That's it. There's no Getty. Let's take a look here at our footprint. Oh, we should do our test, right? Runs our website. We can SSH. What's it running? Well, it includes this little process manager called Runit as part of BusyBox. So that's what we use to run the services. So tiny little process table. And then, of course, systemd cg top. What do you think? 324K. Thank you very much. Enjoy the rest of the show, guys.